This video is about using derivatives in an application situation, specifically to examine motion. So let's talk about position, velocity, and acceleration. If s of t is some position function for an object moving along a straight line, then our instantaneous velocity, often we just say velocity, is the derivative of that position function. So v of t is the derivative of position, that s of t. And then when we talk about acceleration, acceleration is the derivative of velocity. So acceleration, a of t, is the derivative of velocity, which makes it the second derivative of position. Let's do an example. A ball is going to be dropped from the top of a building that is 425 feet tall. Its position function is given by s of t equals negative 16t squared plus 425, where t is in seconds. Let's first find the average velocity from t equals 1 second to t equals 2 seconds. Well, this is something we've done before. Average velocity, when we see that, we should think an average rate of change. And we've done average rate of change. The average rate of change idea was really just the slope between the 2 points. So I have 2 points, 1 comma something and 2 comma something, because I'm talking about t equals 1 second and t equals 2 seconds. So I'll plug both of those in to get their corresponding y values, or s values in this case, since it's called s of t. So s of 1 would be negative 16 times 1 squared plus 425, and that ends up being 409. And then s of 2 is negative 16 times 2 squared plus 425, and if we work that out, it's 361. So I have 2 points, 1 comma 409 and 2 comma 361. So to find the average velocity between 1 and 2 seconds, I'm finding the slope between these 2 points. So that slope, my m, will be, let's see, 361 minus 409 over 2 minus 1, which is negative 48 over 1. So negative 48 feet per second. Okay. Let's look at this next question. Still the same situation, and now we want the velocity function for the ball. So velocity, that v of t, remember that's just our first derivative of position. Our position function is given to us up in the problem. So let's take its derivative. That would be negative 32t using the power rule plus 0. So v of t is just negative 32t. Okay. Keep going. We want the velocity at 2 seconds, 3 seconds, and 4 seconds. We're still the same function, position function. So remember, velocity we just found was negative 32t. So if we want velocity at these 3 times, we'll just plug them in to the velocity function. So at 2 seconds, it'd be negative 32 times 2, so negative 64 feet per second. V of 3 would be negative 32 times 3, so negative 96 feet per second. V of 4 would be negative 32 times 4, so that's negative 128 feet per second. So if we want a velocity at a given point in time, we just need to plug in that time into our velocity function. Now remember, your velocity function is the derivative of position. All right, a new question. What is the initial velocity? Well, initial velocity, initial means at the beginning time. So this is saying what is velocity when t is 0. So we need v of 0. That will be negative 32 times 0, so 0 feet per second. All right, how long after the ball is dropped does the ball hit the ground? So what are we asked for? We're asking how long after the ball is dropped. So we're looking for a time. Does the ball hit the ground? So we want to know, when does the ball hit the ground? Well, that is saying that position is 0, or s of t equals 0. So I want to find the time that corresponds to position 0. Well, position function is s of t is negative 16t squared plus 425. 425. I'm going to let s be 0 and solve for t. So it says 16t squared is 425. So t squared is 425 over 16. And I'll take the square root of each side. And I need to be careful and think about the positive and the negative. So t is plus or minus the square root of 425 over 16. But because I'm dealing with time, I don't really have to worry about the negative. I'm not talking about before this all started. I'm only concerned for times greater than or equal to 0. So I can say that time is, well, I'm just going to approximate. Actually, I'm going to plug that square root of 425 over 16 in the calculator and approximate and say 5.15 seconds. All right. Our next question says, what is the ball's velocity when it hits the ground? So velocity, that means v of t equals what? When it hits the ground? Well, we just discovered that it hits the ground at a time of 5.15 seconds. So what I want to think about is what is velocity after 5.15 seconds? So remember our velocity function was negative 32t. So velocity at 5.15 seconds will be negative 32 times 5.15, which is negative 164.8 feet per second. All right, what about acceleration? What would our acceleration function be? Well, remember acceleration is the derivative of velocity. So it's how velocity changes. So we know that velocity, we found that already, it was negative 32t. So to find acceleration, the acceleration function, we just need the derivative of velocity, which what's the derivative of negative 32t? That would just be negative 32. Feet per second squared is the measurement for acceleration, or the units for acceleration. So what we get here is that our acceleration is negative 32 feet per second squared, which if you've taken physics before, that is acceleration due to gravity. So that kind of makes sense here because we're dropping a ball from the top of a building. Its acceleration should be acceleration due to gravity, unless we are, on a different planet or somewhere different. But we're assuming we're on Earth, so that checks out and makes sense. So what is the acceleration when t equals 2? Well, my acceleration function, I just found out, was negative 32 feet per second squared. Well, at time 2, well, there's nowhere to plug in that t, so this is just that constant function, negative 32 feet per second squared. So no matter what time we're at, over the whole domain of this function, we're negative 32 feet per second squared acceleration.